Okay, so we're going to review for exam 1 and just things that I said before we started the recording here. You will be given an equation sheet with all of the equations that we've covered that you need. But that was 2 statements that we've covered / that you need. So you don't have to memorize any equations. The goal in a science class is not to memorize stuff, right? You can memorize stuff in history. I don't know. In history, you're supposed to learn too, but we tend to take it as more of a memorization thing and not a learning thing. But in the science class, we're learning to understand how things work and why. So you're going to be given situations where you have to say, well, what's going on here? Why does that happen? Or a few problems where you're going to have to calculate something. So you don't have to have any equations memorized. You do need to understand the concepts that we've been talking about and be able to work problems using those.
We don't get that sheet until the textbook.
I have to go through the textbook and compile it. I'll put it to Moodle as soon as I have it done so you can look at it, because it's always useful to be able to organize. I'll have it by chapter, so chapter 1 and the equations. I'm just going to take all the equations listed in each chapter. Okay, so you'll have an equation sheet, and it will be exclusively multiple choice and or true and false, except for one problem. The one problem that won't be will be the one on the scientific method. The one scientific method is going to say, list the 4 steps of the scientific method. Those are the 4 steps that I've been discussing in class, not the 5 steps of the book, but the 4 that I've been discussing. As the book says, there is no one single scientific method that I've been drilling to one. And so it'll have a 1 period, bunch of space, 2 period, bunch of space, 3 period, bunch of space, 4 period, bunch of space. For that 1 period, the first step is observe something interesting. You only need 3 words there. Observe something interesting, not just observe, because you could observe something you really don't care about, and that's not a step in the scientific process. Step 2 needs to have an A, B, and C on it, because step 2 is, and I'll actually write these down here. So step 1, observe something interesting. And step 2 is create a hypothesis that and what are the 3 things it has to do? Okay, explain why observation occurred. I heard that one from Brittany. I know that there was at least one other answer out there. What's another one? Makes testable. Predictions. And what's the final one? It's based on scientific ideas. So you need to have those A, B, and C. It won't have A, B, and C listed, because if I listed A, B, and C, I think that would be too much telling you what to answer. So you'll have to put those in there. Then for step 3, what is step 3? So you're going to test a prediction, I'll say. Don't want to make it too large. So test a prediction of your hypothesis. And then step 4 has 2 options. If hypothesis prediction is correct, then what do you do? Okay, that's right. Back to step 3 with, I'm just going to put another test. It's another test, either testing a different way or testing a different prediction. And what if it fails? So back to step 2. You have more information so you can make a better hypothesis now because you've learned another thing that it's not. If you think about people like, Thomas Edison. Well, I learned 99 ways not to do it, and finally, all I was left with was the way to do it. That's what the scientific method is about. You come up with what you think is a great idea, you test it. If you show that you were wrong, it's not all is lost because you have new information now to go back and make it more correct. What was the reason I didn't like the one in the textbook?
Isn't that one end?
Yeah, that one makes it appear that the process ends, right? You write your conclusion or whatever. But you do have to do that along the way, but you're never done. So it's not like it is in error. It just gives you the impression that you're done one time through and it's done. And it doesn't have the cycling very clear, whereas this has the cycling very clear. And that's part of the, there is no one set correct. So this is the one we're learning. So this is the one question that will not be multiple choice. And that's only the first half. That's going to be 4 out of 8 points. So if you have about 50 questions, all the other questions are going to be worth 1 point. So that means this question here is going to be worth more than 10% of the entire test. Right? So it is a really important question. Why? Because understanding the scientific method is one of the really important things I have for you in this class. So the second half of this is I am going to give you an observation. I'll give you an observation like, let's say, you notice that the days, the sun rises later and sets earlier in January as compared to in July where it rises earlier and sets later in July. So I give you that, and then I say, apply the scientific method to this. So what's the first step in the scientific method?
Observe.
And I just gave you an observation, right? So step 1, you will write that observation. It doesn't have to be verbatim, but it should be, at least an abbreviated form of the observation that I gave you. So it's not tricky. It's just I want to make sure you understand. Yeah, that was the first step, having the observation. Were you going to ask something, Casey?
What kind of hypothesis we come up with for that?
Okay, so that's the next
That's kind
one.
of hard, in my opinion.
The next one is create a hypothesis. So it needs to be based on scientific ideas. It needs to have testable predictions. It needs to explain why it happens. So you can't say, well, it's because I need more sleep in the winter than I need in the summer. Why would that fail?
It's not really scientific, is it?
Yeah, it's not based on scientific ideas. There is no connection we can draw between what I need and why we have sunlight. Right? It may very well be that I need more sleep when it's colder or something, but that's not going to make us have shorter days and longer nights. So the hypothesis needs to be something that's based on scientific ideas. You don't have to have the correct hypothesis, but it needs to be something that's reasonable. Now, for something like this, I know the correct answer. The correct answer is because the Earth is tilted 23.5 degrees for its rotational axis compared to its orbital axis. And because of that, in January, we're tilted, if the sun's here like this, so that the northern hemisphere is tilting away, which means that the part that's in shadow is not going from the North Pole to the South Pole, but it's going from a little closer to the sun, and thus you have less time in the sun. Right, now that's based on scientific ideas, it's based on the motion of the planets, and it makes testable predictions because then we can make statements about, well, if that's true, then we should have a continual variation. We can go to the southern hemisphere and it should be reversed. There's lots of things that we can test. So that's the next step, is how we'll test it.
What, can you remember this example of another one that would still be good, but maybe isn't like the right one? 'Cause
What?
I don't know what
Okay.
like something you would accept that maybe isn't.
I'm trying to think. It's hard to think of wrong things. You know? Well, no, because you're just trying to think of an answer, and I'm not judging you on are you right or wrong. But when I know the right answer, it's hard to say, well, here's a wrong one.
That must be hard.
But, so basically, no, I can't give you an example of a wrong one because I can't think of a wrong one. But
That's okay. See,
you have the ability.
If we said anything in regards to the Earth's orbit, would that be considered okay? They were thinking of sciencey things.
Well,
Yeah.
yeah, it could be dealing with the Earth's orbit. It could be dealing with force of gravity, which of course is part of Earth's orbit. But yeah, it needs to be something that has a connection, something that you can say, because of this, I have this, right? Remember in my explanation I had, it's tilting, so the line that's in shadow is coming over here, closer to the sun than the North Pole, so we have more region in shadow in the Northern Hemisphere, less region in shadow in the Southern Hemisphere, right? That gives us the scientific connection. And, there are other things. Okay, here's a false one that you could come up with. You could say, well, because the Earth is, a lot of people think because the Earth is closer to the sun at one time and farther from the sun the other time, they think that's what causes the seasons.
That's what it is.
It's not. Do you know when we're closest to the sun?
in winter.
January.
Wait, are you serious?
Yeah, like January 5 when we're close to the sun.
Oh my god.
So if the temperatures were based on when we're close to the sun, it would be hottest in January. And it would be hottest everywhere on Earth at the same time if that was the reason. So there's good reasons why it's not. But you could say, okay, because the Earth doesn't have a perfectly circular orbit, then when it's closer, you have a shorter day or longer day, whatever. It's not correct, but at least it has an idea. It's based on scientific ideas.
So like if we did put that down, and then.
You would get the
we'll
credit
fill it all
because
out.
it's the thinking part that I'm looking for.
Okay.
It has to have scientific ideas. It has to be able to make a prediction. So, you have to have those aspects, but it doesn't have to be the correct one.
Okay.
If that was the case, people wouldn't really do science because, I have the wrong hypothesis. I fail, right? No, a hypothesis is an educated guess. It doesn't mean it's the right answer. Okay, now the test part, one thing I want to make sure people don't put for their test is just repeating the observation. Because a lot of people tend to do that. They're all, I'm going to measure the time when the sun rises and sets in January and the time when the sun rises and sets in June. You didn't test your hypothesis, you just checked to see if your observation was correct. So the test needs to be testing a prediction of hypothesis. It's not checking to see if your observation is correct. We're assuming that you observed correctly. So everybody understand that aspect?
Yes.
Yeah. Okay. Now for the final part, if the hypothesis prediction is correct, so you're going to be testing a prediction. It depends on what you're testing. So let's say I took, I'll answer your question in a second. Let's say that I took for my test, based on my hypothesis, it should be just the opposite in the southern hemisphere. And so I go down to the southern hemisphere and I measure when the sun rises and sets in January. When it rises and sets, I don't know if I said June or July, but when it rises or sets there. And my hypothesis predicts that it's going to be just the opposite because if we're tilted toward the sun, the southern hemisphere is tilted away and vice versa. And so when I get to this last one, if hypothesis prediction is correct, I would say if the southern hemisphere has its longest days in in January and its shortest days in July, then I will go back and devise a new test. I don't have to say what the new test is, right? Because otherwise you're going to be going on for a long time. If it turns out that that's not the case, if it's still the shortest day in January and the longest day in July in the southern hemisphere, then I'll have to go back and change my hypothesis. So I've identified what would be in agreement and what would be in disagreement with the prediction of my hypothesis. First Brandon, then Raquel.
You answered it.
Oh, okay. Raquel.
Are you recording this?
Yes, I am.
It'll be okay.
Of course, I'm standing in front, so it's not the perfect recording, but you can hear me. I've checked. It sounds best when I'm behind the beat, so here. Okay, so that is, like I said, that's more than 10% of the test, so that's why it got a special amount of time. Renee.
So for the fourth part, like when we put our hypotheses, tests and whatnot. So are we basically taking a guess at whether we think?
You'll say, for the example I did, what you would write would be, if
Okay.
day in southern hemisphere has most daylight in January, least in July, then back to step 3 with another test.
So for that one, we're just basically explaining what we would do in that case.
Yeah, there are two important pieces here. Number one is you have the condition that agrees with the prediction, right? You don't say if agrees with the prediction, you give the condition that agrees with the prediction, and then going to step 3 to test a different way. And then you would have the second statement. Let's just say if not, right? Because if not what we observed, then to step 2. Right, so you have, this is what I predicted. If that's what occurs, then I go back to step 3 and test differently. If it's not what occurs, then I go back to step 2 and modify the hypothesis because I have more information. And so like if the days were longer in both northern and southern hemispheres, it would have to be something different than the Earth's tilt. Right, it's a definitive test that will rule out my hypothesis with that test if it comes out one way. Any more questions about the scientific method question? All right, then let's review other things. So we started with the prologue chapter, right? It's not even chapter 1, the prologue chapter, which was the introduction. What was in there? The scientific method, right? So I've just been going over the scientific method. Also have the areas of physical science. Now at this point, we're just doing the physics, but you may have a question that asks about the areas of physical science. So that's what we had from the prologue chapter. Then chapter 1, where we start diving into real content. So in chapter 1, we learned about things like forces. Anything that pushes or pulls is a force. We learned about mass. One of your homework questions, I'm not sure if he's graded the submissions that were turned in digitally or not. I've uploaded the submissions that were turned in on paper so you can see your scores. Even if you don't have your grades back, like homework 4 isn't graded yet, you can still look on Moodle and see the answers, okay? So you can see all the explanations and everything there. But you had a question that asked you to rank 4 different objects based on their inertia. Now, it didn't say on their inertia. I think it said on how much force would be required to make it move or make it stop or something like that. But it was wanting you to get to the idea of inertia. So inertia, the resistance to change in motion. It's a fundamental property of matter. We don't have a reason why things have inertia, just that they do. And we measure inertia with mass. So mass is a measurement of inertia. But then there was a part B that asked about the support force. And the support force is the force that keeps something from going through a surface. It's going to be equal and opposite to whatever is pushing it into the surface. Well, in that case, since they were just sitting on the table, force of gravity was down, the support force was up, so it had to be equal to the force of gravity. And the force of gravity is proportional to the mass. Technically, in physics, we have 2 masses. Those are the 2 masses, the inertial mass that you answered for part A, and the gravitational mass that you answered for part B. But that's only a technicality because they've never been found to be different in any way. But when you talk about mass, you'll have people talk about it differently because the gravitational mass, we say, is a measurement of how much stuff is present. It's telling us how its gravitational charges, how it interacts with gravitational force. So make sure you're clear on what inertia is and how it's measured in units. What's the unit of mass? I almost said it. Kilograms. Okay, Aristotelian. What did Aristotle say would happen if I picked this up and dropped it? Now, the starting point is it'll fall down. But then the continuation is why and how. What did Aristotle say? Since this is a review, I'm not going to wait very long. Aristotle said it will fall at a constant rate. That is acceleration of? No. If it's falling at a constant rate, its acceleration is 0.
Oh, yeah.
It'll fall at a constant rate, and that rate depends on how much earth this has in it compared to how much air and fire and water. Because he believed in just those 4 elements. And it made sense to him. And for a couple thousand years, that's what everybody believed. Which seems ridiculous to us because we've grown up understanding better. And so Galileo is the one who said, you know, there's not a natural motion. The natural motion is to be at rest in your natural position. But rather, there's only forces that will make things do stuff. And so there's a force that made it fall, and that force made it accelerate, have a constant change in its velocity. And then Galileo said, let us measure this. And what was the experiment that Galileo supposedly did? Dropping 2 balls of different masses off the Leaning Tower of Pisa to see if it was, you know, the one that has more earth in it, the heavier one, falls at a faster rate and hits the ground much earlier than the other, or if they hit the ground at the same time. Right, that was the whole idea. But he probably never did it, like I said. Most of his experiments were done with rolling things down incline ramps and then using that to understand the process. So make sure you understand the difference in Aristotelian motion and Galilean motion. The forces that we've talked about, I put in the 4 that we had there. We have one more now. So we have a force, anything that pushes or pulls. Force of gravity is one of the fundamental forces. It's a force between any 2 objects that have matter. We measure that gravitational force by measuring the mass, and we have that equation. G, either force of gravity is mg if you're on the surface of the Earth and measure the force between you and the Earth. Or for any other circumstance, force is capital G times mass 1 times mass 2 over separation squared. So you're going to have those equations. You don't have to have them memorized, but you do need to know what they mean, right? So focus on what things mean. So we have gravity, support force. I've already mentioned it. It's the force that keeps me from going through a surface. It always points directly out of a surface. We call the direction directly out of a surface normal, hence it's called normal force. It's not normal as compared to abnormal. It's normal as in normal is the 3-dimensional equivalent word to perpendicular. So we have the support force, friction. Everybody understands friction. You know, if it wasn't for friction, what would happen as I walk around the classroom? I would slide and fall, and it would be a very sad occurrence, right? Well, for me. It'd be funny for you, sure. So friction is what keeps me from sliding. Friction is what makes your car move. How many people thought of that friction is what makes your car move? Most people think, oh no, it's the engine. But if you take your car and you put it on ice, that engine isn't going to make it move. What's missing is the friction that's missing. Now the engine is, going through the drive shaft and whatnot. It's making the tires rotate, and friction between the tires and the ground makes the ground give a returning force to push it forward. Okay, so we got friction there. Finally, tension. Tension is something that acts in ropes or strings, and the direction of tension is always in the direction of the string. And that homework problem that had the pulley, let's draw better lines, that had the pulley, that I didn't look at the picture, if you have a rope that's going around this pulley like this, you have the rope leaving two different places. And so it's going to apply a force on both sides that's equal to the tension. The tension is the force that is being transmitted through the rope. And so in that problem, if the young lady was pulling up with a force of 40 newtons, that means the tension on that rope is 40 newtons. But if the tension is pulling up on both sides, how much is it pulling up on the object? The other way. Twice the tension. Because you have the tension pulling up on the left, the tension pulling up on the right. And so that was the key with that problem. With the picture, the way it was supposed to be, was that she was pulling up on both sides. Now that was in another chapter, but there's our tension. Equilibrium. We had the problem with the gentleman on the scaffolding or whatever. That was equilibrium. We had problem with the painter in his little bosun's seat. Also equilibrium and having to do with tension in both cases. Equilibrium means the net force is zero. Net force, adding them all together. Remember, forces are vectors. They have direction. And so you add all the forces in a certain direction, and if it's an equilibrium, that's zero. And if it's equilibrium, your acceleration is zero. Okay. Speed, velocity, and acceleration. What's the difference in speed and velocity? Direction. Velocity has direction. Speed doesn't. They're both how fast something's moving, but velocity is with its direction. So they're both the distance covered divided by the time it took to cover it. What about acceleration? Because people often get confused. What's acceleration? It's the change in, velocity. Here is a very, very common misconception that I don't think I talked about. The acceleration is change in velocity, yes. So when I take this ball, now while I'm throwing it, there's an upward acceleration because the force of my hand upward is bigger than the force of gravity down. Once it comes out of my hand, while it's going up, what direction is its velocity?
Still up.
Still up, because I said while it's going up, its velocity, which is its motion with the direction of motion, it's up. When it's coming down, what direction is its velocity? Down, because it's coming down. At the very top, what's its velocity? Zero. Because at the very top, it's momentarily at rest. So its velocity is upward. What's happening to the velocity as it's going up? It's decreasing. So what direction is the acceleration? Down. As it's coming down, what's happening to the velocity? And so what direction is the acceleration? Still down, because it's speeding up in the downward direction. So both going up and going down, the acceleration was pointing down. And that acceleration, we know its value. It's g, 9.8 meters per second squared, pointing down. What about the instant at the very tip top? That's the part that people get confused about. That's the very common and incorrect answer. So to understand, I don't ask the question expecting you to have it right. What would the point be of that? So if it's at the top, what was it?
I said, could it be like that on the test?
That's a good thought. It's a good thought, really. But let's think about this. At the top, we established its velocity is zero. If its acceleration is zero, what does that mean about its velocity change? It wouldn't be. So what would the ball do if its velocity and acceleration were both zero at the top? It would just hover. But it doesn't. It comes back down, so it has to have a change in its velocity that's downward. And so during the entire flight, the acceleration was constant, 9.8 meters per second squared down.
Wait, what?
During its entire flight. It had just the constant acceleration because the net force on it was just the force of gravity down. And so we take that force of gravity down, mg, using Newton's second law, which is here, Newton's second law, acceleration is equal to the net force divided by the mass. So if we take mg and divide by m, we're left with g. So the acceleration is g the entire time that it's flying by itself. So it was downward acceleration with a magnitude of 9.8 meters per second squared. Okay, so chapter 2 was understand Newton's laws of motion. The first law, the law of inertia. That just says an object will stay at constant velocity unless there's a force to make it change. The first law is not super important once you get to the second law, because the second law tells you about the acceleration caused by that force. So the second law actually encompasses the first law. Because if your net force is 0, it says your acceleration is 0, which means constant motion. So once you have the second law down, the first law is superfluous because you have the concept of the first law in the second. So the second law is how we relate how much we push and pull on something to how that affects its motion. Then Newton's third law is the one that's very important if you're in Fight Club. Because it says for every action, there's an equal and opposite reaction. For every force applied from object A to object B, there's an equal force applied from object B on object A in the opposite direction. So the example I like to use of this is, in the movies, we see people headbutt people in fights, right? Newton's third law says that if I come and I hit my forehead on Brandon's forehead, the force of my forehead on his is going to be exactly the same as the force of his forehead on my forehead. So we're both going to have that same force and it's going to hurt. Why would people use a headbutt? Number one, they've seen them in the movies and they think it's effective.
They hate themselves.
Because they hate themselves. Good answer right there. There are ways to make it so it's less damaging to you. If you have all your muscles tightened up and you headbutt somebody, your head's not going to snap, but theirs might snap. And when the head snaps, then the brain bounces back and forth, and it's bad for you. So there is that. There is a better way. If I were to grab Brandon and stick my forehead, which is very hard, into his nose, which isn't as hard, sure, it might gouge my forehead, but it would smash his nose. It would cause him more damage because his nose isn't as strong as my forehead. But you know what the bottom line on all this is? Don't get in fights. Okay? It's no way for an intelligent person to solve anything.
Bottom line. Don't fight kids.
Okay, so chapter 2 is being able to use these laws, being able to look at the forces on something and calculate its acceleration. So we had a number of homework problems that were doing just that, to calculate the acceleration given the forces. Question, Jocelyn?
So are you gonna have like first law, second law, third law, and we have to write what each law is?
No. You'll have this equation. I won't give you equations for the first and third because they're concepts that I'll be looking for if there's a question on it. I say if there's a question, I mean, we've got all this stuff to cover and there can't be a question on everything. But I won't say what's the equation. Well, actually, it could say what's the equation for the second law. You would have the second law equation, but it wouldn't say it's the second law. But you could go look through the equation and say, that's it. Question, Larissa?
That's not doing if it was like which.
Yeah, it won't say this is the second law. What equation is the second law, right? Because that would be just a waste of our pencil scratches. Okay, chapter 3, momentum and energy. So we learned about momentum, which is mass times velocity. It's a vector, it has direction. And we learned that change in momentum by Newton's law is equal to the net force multiplied by change in time. And so we called that net force multiplied by change in time impulse. So impulse was force net multiplied by change in time. Momentum is mass times velocity. And by Newton's second law, the change in mass times velocity is equal to force net multiplied by change in time. So the impulse is equal to the change in momentum. What's the symbol we use for momentum? P. That's one you have to kind of memorize because, P, that looks exactly the same. That's as good as it's going to get. Okay, sorry. P doesn't mean momentum to me in any way except for I've memorized that's what it means. And it's a lowercase p because a capital P will be pressure. And a Greek R, which looks kind of like a P, is density. Rho. So, conservation momentum. When should momentum be conserved?
Until an external force.
Okay. When there's no external force, it's going to be conserved. So he said until an external force acts. That would be the same answer. So as long as the net external force is 0, then you'll have conservation momentum. So if I take this ball and I just look at this ball, is this momentum conserved when I let go? Right, after I let go. No, why not?
It's gravity.
It has just one force, gravity, acting down. There's no way momentum is going to be conserved. Now, gravity was acting between this ball and what object? Okay. Now, you can be very technical and say everything that has mass around it, or you can be generic and say the Earth. I'm going to go with the Earth, right? We're all part of the Earth as this goes. So if I make my system both this ball and the Earth, then we've gotten rid of the external forces for the most part. If you want to be technical once again, you say, no. The Earth has a very strong force acting on it because of the moon, and a much, much stronger force acting on it because of the sun. And the sun has a very large force acting on it because of other objects in the galaxy. You can go on and on. For the purposes of a class like ours, we will treat the Earth as if the force of the sun is not there. Right? I know that's not true, but it's going to make a small effect. So if we just take the Earth and the ball and take that as our system, then momentum's conserved. So when I drop the ball, it clearly starts moving down. So what is the Earth doing when I drop the ball? Not moving down. If the momentum initially is 0, when I drop the ball and this has a momentum downward, what's the Earth's momentum going to have to be? It's going to have to be upward, so they add up to 0. So yeah, when I drop this ball, the Earth falls up to meet it. Why don't we ever notice the Earth fall up to meet it? Because what?
Sorry.
Did you say lies?
No, I said we're blind.
Oh, because we're blind. Okay. I thought you were saying that physics was lies, and I was like, wait a minute, that's impugning my feelings. The mass times velocity is momentum. The mass of this is less than a kilogram, right? The mass of the Earth is like 10 to the 24 kilograms. You compare this to the mass of the Earth, this is nothing. And so the speed the Earth has to match the momentum of this is nothing. It's real, but it's not measurable. It's so small. And so the same is true when I jump up. Woohoo! I pushed the Earth down. It went down when I went up. I move more than when I drop the ball because I weigh a lot more than the ball, but by no measurable amount. All right. Then we have energy. It's important that you understand what work is. Work, force times distance parallel. So if I take this, hold on my hand, am I doing work on it? No. Now, my body is internally doing work. That's not what we consider in a physics class. We're just calling it mechanical work. I have a force in this. What direction is the force? Up. My hand is pushing up on it. What direction is its velocity or is its motion? It's not. And so the work is force times distance parallel. No motion, hence distance parallel 0, no work. If I walk like this at constant speed, what direction is my force on it?
That way.
Still up, if I'm at constant speed. So the force is up, what direction is the motion?
Sideways.
Sideways. How much work then? None, because you have to have motion parallel to the force. So that brought us to the examples like, if Casey and I were pushing on the car, and if I was overpowering her, my force is the same direction as the motion, I'm doing a positive work. Her force is the opposite direction of the motion, she's doing a negative work. What's important about work? Well, work gets you money. Okay, work and energy are tightly aligned. Work causes a change in energy or a transformation of energy, because it turns out energy can't be created or destroyed. That's the first law of thermodynamics. Energy can't be created or destroyed. It can only be transformed from one type to another. So when I'm pushing on a car, I'm transforming energy that I've stored up, chemical energy in my body, into doing work. And as I do the work, I'm transferring that energy then into motion of the object I'm pushing. So we have a term for energy in motion, that's kinetic energy. Kinetic energy, 1/2 mv squared. Once again, you'll have the equation. You don't have to memorize that. But you have to understand when things are moving, they have energy. Things can also have potential energy. When I have this up here, gravity has the ability to do work on it. Gravity can make it fall. And so the potential energy is the perfect. I was going to try to kick that to myself, but clearly I missed. The potential energy is how much energy I can get out of a force because of its position. And so remember the pendulum, I had the bowling ball. I brought it up to my chin. What kind of energy did it have when it's stationary about next to my chin? Potential. I let it go. What happened when I let it go? It transformed it from potential to kinetic, but then at the bottom when it started coming up, transformed it from kinetic into potential. Got up here, when it had all the energy back in potential, it stops, comes back, and it just barely missed my chin. Why didn't it hit my chin? Well, for starters, it would have had to have gained energy to hit my chin. Because I started at my chin, it shouldn't be able to come any higher than that unless it gained energy. It didn't quite make it because it lost energy because it was pushing air out of the way. I don't have collisions written down here, but collisions are your classic case of conservation momentum. During a collision, the time for the collision is very, very short. And even if the brakes are applied, the forces between the vehicles or between our little carts are much, much greater than the force of friction. And so the force of friction is negligible, and we treat it like the external force is zero. And so that's why we had momentum conserved during our collisions. But we had elastic and inelastic collisions. You remember the collisions lab? Elastic collisions, the kinetic energy before was the same as the kinetic energy after. Inelastic, you had permanent deformation. Something got bent, and that took away energy, and so you end up with a smaller kinetic energy afterward. Okay, I cover a lot of stuff early so that we don't have as much when we get to them. I've already talked about the universal law of gravitation. Weight is your force due to gravity, is what we usually say. But a better definition is really the force normal necessary to keep you, from falling through whatever. So if I'm standing here, the force normal is equal to the force of gravity. That's why we say both things. But if you're in a satellite, I think the homework problem, it said 94% of the Earth's gravitational force is what you feel if you're in the space shuttle region. You guys read that homework problem? So if you feel 94%, that would mean your force of gravity is 94% what it is on Earth. And yet we say they're weightless. Why?
Because like your surroundings are falling with you.
Yeah. Your spaceship is falling with you. And so compared to it, since you're both in free fall, you're weightless. So make sure you understand those concepts. Trajectories. When I throw a ball, okay, my ball's down there. When I throw a ball, the path it takes we call a trajectory. And that trajectory has constant velocity in the horizontal direction because there's no horizontal forces. In the vertical direction, it's acting just the same as if I throw it up and down. So I throw it up and down, it goes up, slows down, speeds back up. I throw it to Brittany, it does the same thing, except it had a horizontal velocity going along with it that just remained constant. And so we call the shape of that trajectory a parabola. Now we have the Earth has the moon going around it. Why doesn't the moon fall and hit the Earth? We asked this last class period.
Accelerating fast enough.
Not accelerating.
Its velocity's fast.
Yeah, its velocity is fast enough that it is falling toward the Earth, but because the Earth is curved and it's moving, it's just falling around. It turns out in a circle, almost a circle. Technically, it's an ellipse. ellipses are things like this. That's a very exaggerated ellipse. If this is the Earth, where's the moon going to be going the fastest? And you can answer this without knowing beforehand, just by thinking about the work energy we just talked about. Where does the moon have the greatest potential energy? When it's furthest away. So out here, the potential energy is maximum. So what does that mean about the kinetic energy? Its kinetic energy is minimum. It's not going to be zero. But its kinetic energy is minimum out there because it's converted as much of its energy as it can into potential. When it comes back in, here it has potential energy is min. So that means kinetic energy is max. And so it's going to be going fastest when it's closest. That's actually one of Kepler's 3 laws. When Johannes Kepler came up with these 3 laws, he didn't have any of the physics work. He was 100 years ahead of Newton? No, that's not right. He died the same year Newton was born. Anyway, so he came up with these ideas just looking at data, but he didn't have any physics to explain why. And then Newton came up with the physics to explain why this occurs. Okay, then we got to fluids. That's where things ground to a halt because I spent way too long on fluids and then thermodynamics. So we had density. There's our symbol for density, rho, Greek, lowercase r. And density is mass divided by volume. So if I have a bunch of cubes that are 1 centimeter on a side, and they have different masses, that means they have different densities. And the one that has the higher mass is going to be the higher density. Make sure you understand what pressure is, force divided by area. Pressure is hydrostatic. It's the same in all directions, but it always puts a force into a surface that it comes in contact with. So air pressure is pushing down the top of my head, up on my chin. Because pressure gets bigger as you go down, with the equation, change in pressure is rho of the fluid, G times your depth, put H there, then the force that's pushing up on the lower parts of my body is bigger than the force pushing down on the upper parts of my body, giving me a net buoyancy. And so we had Archimedes' principle that said the buoyant force is equal to the weight of the displaced fluid. So if something's floating, of course, its density is less than the material it's floating in, so the displaced fluid is not as big as the volume of the object. If it's sinking, the displaced fluid is equal in volume to the object, but since if something's more dense and sinks, it weighs more, the buoyant force can't hold it up. So we have that Archimedes principle about floating. And so we had force buoyant is equal to density of the fluid, volume displaced, times G. All the equations are given, right? So you don't have to memorize those, but you have to understand what they mean. What's this Bernoulli's principle? It's where I brought out the blow dryer.
Oh, there's the ball, right?
Yeah, I made the ball levitate because when air is moving faster, what happens to the pressure? It drops, right? That's the Bernoulli relation, or Bernoulli's principle. There's an equation for it. We never looked at the equation. But the principle is faster fluid speed, lower pressure, which is why airplanes fly, which is why we can make sailboats that can sail faster than the wind speed, because we have a force that is caused by the difference in pressure. Chapter 6 and 7 dealt with thermodynamics. We had 4 laws of thermodynamics. The 0th law is very simple. It's only there because when they understood temperature more precisely, they realized they needed to define it. The first law is very fundamental. Energy can't be created or destroyed. The second law, the way we said it, heat flows from hotter materials to colder materials. The third law, nothing can reach absolute zero. Make sure you understand the distinction between temperature and heat. They're not the same thing. Heat is a flow of energy. So when heat flows into something, it gains more energy, and temperature is a measurement proportional to the average kinetic energy. So when heat flows in, the temperature goes up, and that brings us to things like, well, temperature change when heat there. Make sure you understand what thermal expansion is, explain how that occurs, and why water is unique. I have the water uniqueness here. Why water is unique, why water because it's different, we can have life on Earth. If water acted like iron, we wouldn't even have life on Earth. We would be a popsicle. Also, make sure you understand that greenhouse effect. Without the greenhouse effect, we would also be popsicles. 3 mechanisms for heating: conduction, contact, convection, an intermediary that carries energy from point A to point B, radiation, waves. And finally, we talked about electricity. And all we talked about there was there are 2 types of charge, positive and negative. The electron is the basic negative charge. The proton is the basic positive charge. And Coulomb's law allows us to calculate the force between charges. Remember that likes repel, opposites attract. And that equation for the force is just like the force of gravity. Force electric is K Q1 Q2 over R squared. We didn't talk about current or resistance or magnetism, so those topics won't be on the test. Obviously, neither will optics because we didn't do optics.